was the last time that you ate a grape? They're about the size of your thumb, depending on the size of your thumb, right? Now imagine that if you shrunk the entire size of the Earth to the size of a grape, you would have a black hole. Now can you imagine that? The entire Earth being shrunk into the size of a grape? How does somebody even figure that out? That the Earth to the size of a grape in that sort of ratio becomes a black hole. And so I wanted to today explain to you guys a little bit about black holes. But I realized that you can't really explain any singular aspect of black holes because they're this big and entire subject that you can't talk about one thing without explaining everything else, and that's the problem that I ran into. So I decided I would tell you guys a little bit about everything instead. So this is a black hole, well at least an artist's picture of a black hole, and I think they look very cool, which is why I want to talk to you guys about them. So this here is the black hole itself, is this little black dot right here. And if you ever heard some of these definitions that I'm going to be talking about, like accretion disk, quasars, blazars, lots of fancy words. These right here are quasars and blazars, giant streams of light. This is just a disk of matter that surrounds the black hole that feeds it like all of its food. And this is a giant star that's sucking all of the energy out of to go into it. And I think all of that sounds very cool. So first, what is a black hole? NASA says that a black hole is a place in space where gravity pulls so much that not even light can get out. And you have to consider, does that definition do it justice? No, I don't think it does, because it leaves so many question marks. A black hole is one of physics' biggest question marks. Caltech theorist and black hole expert Kip Thorne said that like unicorns and gargoyles, black holes seem more at home in the realms of science fiction and ancient myth than in the real universe. You have to consider that something that exists in our universe seems more akin to something in science fiction than our world. Can you imagine that? To me, I obviously think that's very cool. And so the thing is that black holes are still an idea. So we have this, which is a diagram of all the different kinds of things that you see in a black hole, like the previous one, but with more definitions in it. So this, like I said, is the accretion disk. This is the black hole, and then these are the blazars and quasars. And you see they're pointing at the same thing, because we have different names for the same things viewed at different angles, because the way you do astronomy is all you can do is stand here and look in a very, very big magnifying glass to see something from really, really far away. So as I said, I had a list of definitions: quasars, blazars, singularity, event horizon. If you don't know what these words are, that's okay. Scientists didn't know what they were, so they just gave them a name. And that's how a lot of science is done. For instance, you think about Kepler's laws, which are how we define orbital mechanics, which is how things move around in space. The first one is that the orbit of a planet is an ellipse. The second one is that as it moves, equal areas of time are drawn out in equal areas of space. And the third one is that its orbit is equal to its time orbit. And so he didn't know how to do the math for that, so he made it relative. So you have the astronomical unit, 1 AU is the distance from the Earth to the Sun, because he just made it that. So everything's relative to AU because he didn't know the distances, so he just made them up. And so why is that important to you guys? Well, you have to consider how you have your cell phones, your technology. You have orbiting satellites around the planet Earth that are based upon Kepler's laws. They get up there, and that's how we have them orbit without falling into Earth or crashing into other things, so we have to keep them steady. And so I'm going to switch gears a little bit and tell you guys about another cool concept called general relativity. And so this, if any of you have seen a weird diagram that looks like this before, it's about general relativity, which is about gravity. Now this doesn't quite look like the gravity you or I know. The gravity you or I know is just, you drop an apple, it hits the ground. But gravity is actually, as Neil deGrasse Tyson says, a force in the curvature of space-time. So this is actually be a space-time diagram, and gravity can go up and down into it. So you'd imagine back down, way down here, it would be a black hole. And so the closer and closer that you get to it, you just end up falling in and you can never get back out. And so you have to consider that if you see that, it looks like it goes on infinitely. So falling into a black hole is like falling into an infinite well of gravity. But infinite is a word that we don't like in physics because it doesn't mean anything. What is infinite? There's no way you can define that, and so we don't like it. And there's also the case where there's nothing one of the ways in which we define black holes is just this big well of nothingness. Like nothing is another word we don't like because it also means there's no way to explain what it is. It's just a big question mark. Infinities don't exist in physics. We use them to explain things we can't understand, but we don't actually know what they are. So it's just kind of this big band-aid we put on things that we're trying to explain. So the last fun thing I really want to talk to you guys about is what would happen if you entered a black hole. There are a couple of major ideas that people have, but the number one is called spaghettification. Now, if you don't know what that is, I think it's very cool. It's the idea that, as David Eicher said in the Astronomy magazine, a stellar black hole would have sufficient gravitational force such that it would pull you into a miles-long string of particles. Or, you look something like this. As you got closer and closer to the black hole, like say you were going feet first, the force on your feet is so many infinitely times larger than the force on your head that it pulls you into a noodle the closer and closer that you get. And so that is spaghettification, but we don't actually know if that happens. Sadly, we've never launched somebody into any black holes, despite what Interstellar might say. And so we don't actually know what's inside. Another theory is that you just be annihilated, you just disappear, and well, you can't disappear, that's the whole point, is that you can't disappear. You'd be annihilated into this string of information, and then you just exist there, inside the center of a black hole, which is nothing but everything at once, because we don't actually know what it is. And so that is what would happen if you would enter a black hole, which is very exciting. And so you may again think, why is this important? Why do we need to go back into this? Why do we need to study these sorts of things? And I want you to consider the idea about physics in general and why that is important. Because if you consider each hour, 430 quintillion joules of energy are produced from the sun that hits the Earth. The entirety of the world's population in about a year produces 410 quintillion joules of energy. So in 1 hour, the sun could power the entire world's population for a year. So imagine if we could use or harness that energy. And no, that doesn't necessarily have to do with black holes because that's the sun, but if you consider black holes, they defy the laws of physics as we know them. And if we understand black holes, we can rewrite and redefine the laws of physics, and therefore finding out a way to harness the energy of a sun doesn't seem like it'd be so hard anymore. Imagine what we could do once we unlock the biggest secret in space.